In the last video, we learned what a periodic table was and that we group things in a periodic table based on their characteristics and shared characteristics. We then understood that the characteristics of elements are determined by how the electrons move around the elements. And we started building our table here with our first simple element, element number 1, and then we added a proton and an electron, and we had element number 2. Now that we have 2 electrons, we need to discuss how those electrons interact with each other. To do that, we go back to our rules here and we look at rule number 3, and that is that electrons repel other electrons. They're attracted to the protons, but they repel other electrons. They really don't want to be near other electrons. Kind of like when you have 2 magnets, they kind of push away from each other. Same way with the electrons. And to give you a better feel for this, I have an analogy, which is just a story that is about something else, but it will kind of describe what's going on with these electrons. And it will give us some language then that we can use as we go forward to understand in more detail how these atoms are put together. Okay, in our analogy, we start with this park, and this we can call the proton park. This is where proton kids come to play. Okay, so this first proton kid is in the park here, and outside of the park is this ice cream truck. And ice cream trucks are attracted to kids because they want to sell ice cream to the kid. So they're attracted to the kid. Now the problem is that this ice cream truck, which is moving, cannot drive through the park. You can't go through the park, you have to go around the park. So the ice cream truck drives around the park trying to get the attention of the kid to come and buy some ice cream. Okay, so this is kind of like the electron moving around the nucleus that is the park. Okay, now when we add another proton kid to the picture in the park, and then because there's now a couple of kids, that attracts another ice cream truck saying, wow, there's more customers here. I want to get my opportunity to sell some ice cream. So these 2 ice cream trucks can drive around the park trying to get the attention of these proton kids. Okay, now these trucks are actually driving around this neighborhood that surrounds the park. They're driving on the streets of the neighborhood and they're trying to get their attention. So they're driving around the neighborhood again, attracted to these protons. Now this is working fine at this point because there's enough room in this neighborhood that these trucks can drive around and they don't have to get too close to each other. The problem is if the third proton kid shows up to play in the park and that attracts yet another ice cream truck wanting to sell ice cream here, the problem is this neighborhood is getting too small to have, well, it's the same size, but there are too many ice cream trucks trying to drive around in this small space. So these trucks are very sensitive to each other, and there's some tension here because they don't want to be near each other. So this guy may move trying to find some space, but now he's too close to this guy. Okay, so eventually he realizes he's just going to have to move and get out away from these other ice cream trucks in the neighborhood. And the simple way of saying this is that there's only room for 2 ice cream trucks in the neighborhood. So if there's more ice cream trucks that want to move around the park, they have to move around the park further outside of the neighborhood. So here we have the 2 ice cream trucks in the neighborhood driving around the park, and here's our third ice cream truck out in the city. And so he can drive around in the city and drive around the park while the 2 other ice cream trucks drive around in the neighborhood, and there's plenty of room and they don't run into each other. As a matter of fact, the city is a big place and it can hold several more ice cream trucks. As a matter of fact, 8 ice cream trucks can drive around in the city without running into each other and getting too close to each other. So the city will hold 8 ice cream trucks. Okay, now when the 9th ice cream truck shows up, there's this problem because he's too close to the other ice cream trucks, and this tension says, no, you can't be here, we're full. There's not enough room for you, Mr. 9th ice cream truck. So he's going to have to go outside of the city. So in the city, there's only room for 8 ice cream trucks, okay? So this guy has to go outside of the city. So what is bigger than a city? And that is the state. So now that we're out at the state level, we can accommodate many more ice cream trucks that can drive around. There's plenty of room that 18 ice cream trucks can drive around without getting too close to one another to cause any problems. Now when the 19th one comes in, it's not going to fit. So it's going to have to go out to some space larger than the state. Maybe that's the country. And then we can go to the planet and to a solar system and galaxy, or however far you want to take the analogy. We're going to stop the analogy here and get back to talking about our elements. We have our two elements here, and I'm going to redraw these a little bit different. These are a Bohr model that I got from Wikimedia Commons, and it's nice because they're all the same, and we'll go ahead and use these going forward. But now we can bring in our third element. And as we bring in our third element, you'll see it now has this third electron out here. And the first two electrons are in the neighborhood, as they were for the first two elements that we had. But this third one is out here in now what we call the city. Okay, so if we were going to add this to the chart, we already listed our first two in what we call the neighborhood row because all their electrons were in the neighborhood. And now we're out of room in the neighborhood. And just like when we had listed our numbers and we ran out of numbers and we had to do something different, we use that as a point to wrap around and start our next row. So this would be a good point to wrap around and start our next row, and we'll call it the city row because this one has an electron out in the city. Okay, so we can add that to our chart here, and then we can bring in our next element, which has two electrons out in the city, and we can add it here, and we can continue to add protons and electrons as we move these different elements until we have the 8 electrons out here in the city. So we have 2 in the neighborhood and 8 out in the city. And as you recall, the city would only hold 8 additional electrons. And so if we were to add one more, we'd have to go further out. Now we're starting to build a table here because you can see now that in this column we have 1 electron in the outermost shell or the outermost ring. And in the next column, that represents 2 electrons in the outermost ring, and then 3 in the outermost, all the way over until we get over to the last element here of this one, which has the 8 in the outermost. And again, once that is full, if we add another proton and electron, we'll have to move out further and go to a new ring, and we can call that the state. So let's bring in our next element here. And you can see now that we have this electron in this outer ring here. This is in the third ring out. We call it the state row here. And so we can add that to our table here, keeping consistent with having 1 electron in the outermost ring there. And then we can continue to build this table out, adding 1 more to that ring all the way out until we get over here on this side of the table, where again we have 8 in the outermost space. Now, I keep calling these rings, or the row, the neighborhood, the city, or the state, but these are also known as shells. So this could be shell 1, which is this neighborhood shell, and then the next ring out is the space that's further out, we call shell 2, and what we were calling the state, which was out a little bit further, we call shell 3. The other thing to note about the way this is drawn here, when we change to this picture, you'll notice that we no longer are showing the count of the protons inside, but instead there's a letter. And that's because these elements actually have names. We don't just call them element 1 and element 2. They've been given names like hydrogen and helium and so forth. And so we could choose to represent our table, instead of using our E numbers, we could use these abbreviations for the names of those elements. Our chart now shows the table with the abbreviations of the names of the elements. And next we're going to start looking at adding our the next element. And we're going to need to talk about what happens when we want to add 1 more electron to this outer ring. But in this video we are out of time, so we'll pick up there on our next video.